Hello, I'm Griffin.
I'm Olivia.
Bizzie. And I'm Lucy. And at Six Flags Great America, we studied the American eagle. In this video, we will determine the height of the initial drop, analyze energy transfers, find the initial velocity without friction, and determine the work done by friction.
We will also determine the length of the track and determine the frictional force using work and the net force.
Using the Where in the Park list, we chose to analyze numbers 2, 4, and 9.
We hope you enjoy our presentation.
First, we analyze the motion of the roller coaster as it goes down the ramp to display a point in the roller coaster when the velocity and acceleration are going in the same direction, addressing number 2. The effect of this is the speed is increasing in the direction the cart is moving.
Next, we analyze number 4, the effects of an applied force and a frictional force acting in opposite directions. This occurs while the cart is going up the initial ramp. As the applied force pushes this cart to the right and up this ramp, friction is pulling it back from the tracks and air resistance also pulls it back. Lastly, we observed number 9, when gravitational potential energy is being converted into kinetic energy. The maximum gravitational potential energy is when the carts are at the peak of the roller coaster, and this energy is then transferred following the law that energy cannot be created or destroyed. It then transfers to kinetic energy as it begins its descent down the ramp. The maximum kinetic energy is found at the bottom of the coaster once all the cars are level out. This is not visible due to the American Eagle going underground. We calculated the height of the roller coaster by taking two angle measurements 2 meters apart. We found the high point of the roller coaster to be 15.4 meters, although it should be around 38.7 meters. We calculated the low point of the roller coaster using a similar method of collecting two angles 2 meters apart. We found the low point to be 1.9 meters underground, however it should be closer to 6 meters.
We use the average velocity and the time to determine the length of the track to be about 100 meters. Here is a free body diagram displaying the forces occurring during the downhill of the roller coaster ramp. The calculations to the right depict frictional force using net force. Below the free body diagram are calculations to find the frictional force with work.
Here are the calculations we used to find the ideal final velocity of the carts. Here are the calculations we used to find the work done by friction. To find this, we subtracted the kinetic energy actual from the kinetic energy ideal.
At Six Flags Great America, we learned the different effects a roller coaster cart is under as it travels through different stages.
As it first goes up a ramp, the applied force and the frictional force are acting in opposite direction. Then, once it reaches its peak, the gravitational potential energy gained throughout the ride is actively converted into kinetic energy.
Lastly, as it goes down the ramp, the velocity and the acceleration are in the same direction.
From the roller coasters we rode at Six Flags, the American Eagle had the greatest amount of inertia due to the change in acceleration and the lack of secure restraint since the ride only had a seatbelt and a single bar.
During this project, I learned that it is difficult to accurately determine the height of the roller coasters using an app to get the angle measurement due to the inaccuracy of the degree measurements.
During this project, I learned how, although the ideal and actual velocity were very close, the work done by friction played an immense part in the energy.
During this project, I learned how much inertia plays a part in creating the thrill in a roller coaster because your body wants to move in a different direction while the cart turns in a loop in the coaster. I learned that roller coasters are great ways to study physics because they exploit kinetic energy and gravitational potential energy to their extremes throughout the ride. Thank you for watching our presentation. Bye!
Woo!